Right, class, I think we better start now. Can you hear me before we start?
Yes, doctor.
Yes, doctor.
Okay, right. So I'm going to present now. Can you see my screen?
Yes,
Okay, thank you. So previously in lecture 3, we have deals with a method of elimination that we call as Gauss elimination. However, in this particular week, we are going to learn about the LU decomposition and also metric inversion. But I'm not really sure if we can uh, do the metric inversion today because the LU decomposition would be quite a lot. There's a lot of things that you need to learn about LU decomposition. So let's say that we cannot really finish by today. I might post a video on it. However, regarding LU decomposition, it actually deals with a class of elimination method that we call as LU decomposition. So LU stand for lower upper decomposition. So LU stand for lower upper decomposition. And why do we need LU decomposition? Right, so elimination step is, if you refer back to our slide in the previous lecture, elimination step is quite time consuming and therefore we can use LU technique where it's involved only operation on the matrix coefficient. So if let's say if you remember previously, if we have matrix like this, so X column vector is equals to B. In order for us to calculate or solve AX for this system, if we use Gauss, we will need a lot of pivoting and also a lot of steps. However, if we use LU decomposition, we only going to involve operation on the matrix coefficient on A only. So in a way, it's a bit time consuming, and in terms of computation time and also effort, it will be less demanding compared to the Gauss elimination. So here we're going to focus on showing how the Gauss elimination can be implemented as an LU decomposition. Actually, it requires the same steps. However, LU decomposition would have less demanding steps. Right. So we move to LU decomposition. For example, if you refer back to our Gauss elimination, it solves a system of linear algebraic equation of this. So this, if we use Gauss, it will solve the excess value for this particular system. And it has, or it consists of two main steps. The first one would be forward elimination. And the second step would be back substitution. So this one is for Gauss elimination method. if we refer also back to the previous slide, we will see that forward elimination actually consists of a bulk computational effort or large system of equation, especially for large system of equation. So the highest effort would be on forward elimination. By introducing LU decomposition methods, it actually separates the time-consuming elimination method here. So on this particular step, if we use LU decomposition, it will actually separate the time-consuming elimination of the matrix A from the manipulation of the right-hand side of B. So we don't really need this part here. We're only going to focus on B. So on matrix A, on coefficient matrix A. So if we use LU, we're going to only focus on matrix A. And this matrix A, we're going to decompose it into two parts. So the first one would be lower triangular system, and the second one would be upper triangular system. So after we have decomposed matrix A into these two parts, we can actually evaluate the value of X in a pretty much efficient manner. And bear in mind that LU decomposition, similar with Gauss elimination, actually requires pivoting to avoid division by zero. However, in this particular class, we will defer this issue in order to focus on the fundamental method of LU decomposition. So this is a bit similar with Gauss, where the pivoting, the issue of pivot actually occur. However, we're going to defer it in order for us to focus on the fundamental issue. Now, so we are going to limit the following example to 3 simultaneous equations. So the result can be directly extended to n-dimensional system. However, we are going to focus on 3 by 3 matrix. So for example, if we have this equation, this system of equation, so we can rearrange equation 1 into this. So we can rearrange it. So the B here, the column vector will move to the left-hand side. To become equation 2. And then suppose that equation 2 can be expressed as an upper triangular system. So we are going to assume that this equation can be expressed or represent as an upper triangular system, where it can be written as and we represent this as equation 3. So equation 3 actually can be expressed in the metric notation, and we can rearrange it to equation 4. So if we try to put it in metric notation, it will be something like this. And this would be equation 4. And then after that, we are going to assume, so there will be another lower diagonal matrix with 1 on the diagonal. So we are going to assume that there will be an L matrix where in the diagonal it will be consist of 1. So L21, L31, L32. So this is 0. So in the diagonal, the value would be 1. And we denote this as equation 5, where this equation 5 actually has the properties of if we multiply equation 5, if we multiply the value or the matrix L with equation 4 here, we will get actually the value of equation 2. So what we are, if we try to substitute everything, we will get equation 6. And this is equation 6. So you just substitute equation 5 times equation 4 equals to equation 2. So if you try to do that by yourself, you will get equation 6. And from the matrix multiplication rules, if we try to do it, if you try to see it thoroughly in equation 6, you will see that matrix L, the multiplication of matrix L and also matrix U here, this part, this color, this one here, is actually the same with A. And D here, because this is L times D is equals to P, because negative L, matrix L's multiplied by the column vector is equals to B. So in a way, you can deduct that the value of a matrix L multiplied by matrix U is actually matrix A, and matrix L multiplied by matrix D is actually matrix B. So this first one we denote as equation 7, and the second one we denote as equation 8. So as you can see that from this particular step, there are actually two main steps. It's a bit similar to Gauss, where this is a representation of what we have just done previously. For LU decomposition, we actually have two main steps. So the first one would be LU decomposition step. Where the matrix A is factored or decompose into two main parts, which are matrix L, which is the lower, and also matrix U, which is the upper triangular matrices. So we're going to have two L and U. So if we try to put it in much simpler representation, we can see that first, if we have a set of equation that we need to solve for x. So if let's say that we have something like this. So first thing that we need to do is to decompose this matrix coefficient into two. The first one would be upper triangular matrix, and the second one would be lower triangular matrix. And then the second step would be to substitute, would be the substitution step, where we are going to use the matrix, the matrices that we obtained previously, L and U, to determine the solution of x. Solution of x, where the first thing that we're going to do would be to generate an intermediate one. So for the first step of the second step would be to generate intermediate. Intermediate vector D by forward substitution, and the second step would be substituting D, vector D, into equation 4. If you refer back, in would be the matrix of this minus D, in order for us to get x. So in a way, in terms of graphical, we can represent it after we have obtained these two here. First, we are going to get the value. We're going to substitute it into the previous equation. So L times vector D equals to B. So B, we get it from top here. So here, we're going to get the value of D. So from here, we actually can get the value of D. And then from that particular value of D, we can actually get the value of X. So this is equation 4. So we get this in order for us to get X, X1, X2, and X3, assuming that we have three values, unknown values of X's. So this one, if we try to compare it with Gauss elimination, this part here is actually forward substitution. while this part here is actually backward substitution. So this is a graphical representation of LU decomposition. So it looks a little bit not easy, but it's look less complicated compared to the Gauss elimination. So even though right now you might see that it looks like Gauss elimination is quite unrelated to LU decomposition, it actually can be used to decompose A into U and also L. So if you refer previously to the Gauss elimination, so this would be the graphical representation that we have derived previously. So if we try to look at the forward elimination step, it actually used to reduce the original coefficient matrix to an upper triangular format. So if you refer to the Gauss elimination, where the first elimination is actually it reduced the original matrix, the original coefficient matrix there, into upper triangular system of L. So this is, if you refer back to the previous equation, previous slide number, lecture number 3. So remember that single prime means it only have one modification, while if we have double prime, it will require double modification. So although it might be not be as apparent, the matrix L is also produced during this step, because if you remember that for L, so if you remember that in order for us to get L, it's not really apparent, it's not like crystal clear that you get L, but if you remember, after in the Gauss elimination, after you obtain the upper triangular format, triangular system, matrix system, we're going to see that A11, A21, A31. So this is matrix A, coefficient A. B1, B2, and B3. So this would be the first, if you remember, the first step in Gauss elimination is to multiply row number 1. So this is row number 1 by the factor of this. So we are going to multiply row number 1 with the factor of this in order for us to subtract the result and the result from the second row to eliminate. So after we get that value, we're going to subtract it with the second row, subtract with from the second row to eliminate A to 1. So similarly, the row number 1 is then multiplied again by 3, 1, a factor 3, 1. So this 3, 1 is actually the ratio of A31 over A11. And then we are going to subtract it from the third row to eliminate A31. And then, so after we already done, so this one is the first modification. So if you remember, after the first modification, this row, the second row, will become A prime to 2, A prime to 3, and so on. So this is our first modification. So the final step is then to multiply the second row by this vector. So this is the third modification. And then we are going to subtract the result from here, from the modified third equation, third row, to eliminate. Oops, I don't know what happened here. So eliminate A prime 3, 2. I'm not sure what happened here. I think there's something wrong. Oops. Not sure. I think there's something wrong with my writing tablet. Sorry about that. So anyway, since this, hopefully this is recorded. I think I've recorded it. So after the elimination, we actually can write A, the matrix A. After we have done the elimination, we actually can write A as, so this is A as A11, F21, F31, A12, A prime 22, A3, F32. So this is F, A13, A prime 23, and also F double prime 33. So we are going to denote this as equation 10. And then 10 is actually represented by the decomposition of A. So here we're going to see that A, the matrix A, is actually the multiplication of the lower triangular system prime by the upper triangular system. So U here is actually, I think there's something wrong here. U here is actually, I'll just write. Yeah, there's something wrong with my writing tablet, sorry. Okay, so this is the writing. Okay, so as you can see that this one is actually, so matrix A is actually composed from, okay, we can see that it's actually composed from L and also U, the upper and also the lower triangular metric system. So L here is A1100, A12, A prime 22 and 0, A13, A prime 23, and A double prime 33. So this would be the lower triangular system, where if you refer back to this, you will see that this part here is actually 0. So that's why we call it as lower triangular system. And then we're going to see the upper triangular system. Where upper triangular system, you will see that the diagonal value of that particular diagonal element is equals to 1. while the lower factors here are actually represented by the factors that we have used to decompose the value previously. So going to have 0 here. So these two elements are quite it's quite useful for us to find the value of x's. So for example, if we have a similar equation that we have used before, using Gauss elimination as a way or method to solve for x. So for example, if we refer back to a set of equation that we need to solve. So for example, so this is an example. The same example that we have used previously. So 3x1 minus 0.1x2 minus 0.2x3 equals to 7.85. Zero point one x1 plus 7 x2 0.3 x3. So this would be the second equation. Okay, right. So we actually have a 3 by 3 matrix, and if we try to convert it into metric notation, we actually will get this. So we actually can get this metric notation for a 3 by 3 equation, algebraic equation. So we need to solve for x1, x2, and x3. So what we are going to do first is by using, so the first part here, we're still going to use Gauss method, where we're going to use a forward elimination in the Gauss method. So first thing first, after the Gauss elimination, we're going to get the upper triangular system. So if you refer back to slide number 3, we, after forward, after forward elimination in Gauss, we will get the upper triangular system of 3 this is so this is after we have done the forward elimination. So the factors that employed to obtain the upper triangular matrix U matrix here can actually be assembled into lower triangular matrix. So if you remember, in order for us to get this metric, we're going to have to use factors and that will be used to get 0 here. So the factors here will be multiply this value, the first row will be multiplied with the factors and then subtracted to that particular row that we're going to eliminate, that we wanted to eliminate the value of. For example, if we wanted to eliminate the value of x1 from the second row, therefore we are going to multiply the factor by the first row and then subtract the the result from equation 2 or the second equation. So from first elimination, we will get the factor of 2, 1 as 0.1 divided by 3. So 0.1 divided by 3 to get 0.03333, 6 significant digit. And then for F31, so this is the third row. So F31, the third row, we are going to use 0.3. So 0.3 here divided by 3 so that we can see the result subtracted from equation 3. And we will get 0.100000. So this would be for first elimination. From the second elimination, F32, we're going to see that 0.1919, this is actually the value that we get from the first elimination, divided by 7.00333. This value also we get from the second elimination, and we will get this value. So from there, we will actually get the lower triangular matrix as 0.03333. So this actually corresponds to this. And this 0.1 correspond to this. So since this is an upper metric system, so the top one will be 0, 1, and 1, 0. And this part here would be the value here that we get. So negative 0.027130. So that's how we get the value of the lower matrix, lower triangular matrix. So remember that from the previous slide, it mentioned that matrix A is actually the multiplication of its lower triangular matrix and also its upper triangular matrix. So here This is 1 and 2. So it's actually 1 matrix 1 times matrix 2. And from 4, if you refer to this equation, so this is equation 4 here. From 4, it actually says that this, and we actually can substitute the upper triangular matrix that we have already obtained to get the value of D. However, as you can see here, D is in order for us to get X. So, however, in this particular equation, we actually see there are two unknowns, two rows of unknown. The first one would be X. We don't really know what is X, what are the values of X's, and also the intermediate values of D. So we don't really know these two vector matrices. So in order for us to, if you refer back to the graphical representative of LU decomposition, we need to get the value of D in order to get X. So in order to do that, from equation 8 that we have derived previously, we know that L, the lower triangular matrix, multiply by the intermediate matrix is equals to B. So if we try to write this down, so it's only 6 significant digit. Equals to the value of the coefficient here, where this is B. So it's 7.85, negative 19.3, and 71.4. If we try to look at this metric by direct interpretation, we will see that D1 is actually 7.85. So we can then substitute D1 into the second row to get, so I just get using the one. So from the previous matrix system, we will know that D1 is equals to 7.85, while if we try to substitute D1 into the second equation, we will get D2 as actually negative 19.5617, and we can also substitute D1 and also D2 that we have calculated into the third row, the third equation. To get 70.0843. So in a way, D is the vector D, the vector matrix D is actually 7.85, negative 19.5617, and 70.0843. So if we turn back to the equation 4 that we previously stuck, so this is equation 4, we actually can solve for x. So this u, so this is u times x's. So this is the value of the x's. So d. So this is substitute the one that we have obtained previously. So from there, if we try to do a back substitution, so this is quite, this is a bit easy. So 10 x3 is equals to 70.0843. You will get x3 nearly, and then substitute into the second equation, you will get x2 as negative 2.5 and x1 as 3. The value that you get might be a little bit discrepancy. There will be some discrepancies when you try to get the value of x1 and x2. However, in your examination or in your test, if the discrepancy is within 5%, it will be okay. So it will be, the answer will be right as long as the discrepancy is within 5%. Right. So we only have about 9 more minutes. So for the next class, I think I'm going to post a video on this, on error analysis and also system condition. So if you remember, we also have inverse of a matrix. So inverse of a matrix actually provides a means to test whether that system are ill conditioned or not, whether it's appropriate for further numerical analysis or not. So if it's ill conditioned, we cannot really use numerical methods to solve that particular system. So in a way, inverse of matrix will show us whether that particular system is suitable for numerical methods or not. So this particular topic, we are going to cover it in another video. I don't think that we can cover it now since we only have like about 7 minutes left. So I'm going to post that particular video soon. And another thing would be your previous tutorial. I think I'm going to discuss about your previous tutorial on Friday morning, 9 o'clock. And we're also going to have another tutorial on Gauss elimination using numerical methods, using MATLAB. to compute for the value of x's. Is there anything else that you wanted to ask?
Doctor?
Yeah, I cannot hear you. Sorry.
Can you hear me now, Doctor?
Yes, yes.
Yeah.
Who is this?
Shikai.
Yes.
Can I ask the date for the test, the midterm?
Midterm.
Yeah.
Midterm would be the 7, if I'm not mistaken. If we refer back to your, it would be 7, right?
Week 7, is it?
Yes.
All right. So it's next week, is it?
Next week. Yeah, I've forgotten already because I'm so busy. Okay. So by right, then the semester, the mid-semester should have covered up until numerical and numerical differentiation and integration. So I think maybe we can postpone it until you have done all the topics on numerical differentiation and integration. Otherwise, we only have like 3 topics for your mid-sem. What about your other subject, Shukai?
Max is engine max is like next week, and then some is at PAC 2 is in week 8, and the rest still not sure.
When is Raya actually?
Oh, this maybe sem break week 10.
Week
Is
10.
it? I'm
So
not that sure.
Can we do that before Raya?
So it's week 9.
Yeah, because I don't really want you to have like a lot of tests during that particular week. So I don't want to overlap with other subject.
Okay, so I think it's up to everyone else.
Yeah,
okay.
yeah. So what about everyone else? Because I don't think that you want to have tests after Raya, right? Otherwise, you cannot concentrate during your Raya.
I think week 9 is fine.
Week 9, huh? Any objection to week 9? No, huh? Okay. So in that case, this is week 6, is it?
Yes, doctor.
Yes,
Yeah.
doctor.
Okay. So in order for you to prepare you for mid-sem test, I'm going to give several assignments, but this assignment wouldn't be. I don't think that I'm going to. I don't think that I'm going to ask you to submit it because but I will see. I will see if you remember previously in the planner, your continuous mark is about 50% over 100, while your examination mark is 50%. So this is a bit different with your other subjects. So 50-50. Your test is around 30%, which is it consists a lot of marks, and 10% would be from your tutorial that you submit after your MATLAB session. So that would be 10%. So we are going to have 10 tutorials, 10%, and another 10 would be from your assignment. So 10%, this 10%, I'm planning to get it from you, but I'm not really sure when should I give your assignment back, because I know that you are quite packed. Do you have a lot of assignments due soon? Anyone? Ida? No? Farah? No one? Hello?
We do have assignment.
You don't have assignment at all?
We do have, but The due is later by this.
Oh, okay. And in that case, is it possible if I give you 2 assignments? So these 2 assignments actually will prepare you for the test at the end. So you only have 1 test, but the first assignment will prepare you for the only test, and then the second assignment will prepare you for your examination. Is it okay? Yes, class?
Okay, Doctor.
Okay?
Yes, Doctor.
Okay, so I think I'm going to have a look on the dates, but as mentioned, as discussed previously, we are going to do the test before Hari Raya, before the Eid, and hopefully I can give you the assignment like 2 weeks before it's due date. So I think that's it. Is there anything else you wanted to ask? I noticed that several of you are not going to be here on Friday. That's okay. In that case, I'm going to I will try to record the tutorial and post it in Spectrum later. Anything else?
No, Doctor.
No? Okay. I think that's it for today. Thank you for coming to my class. I'll see you on Friday then. Okay,
Thank you,
bye.
Doctor.
Bye.